So, Moritz.
Hi. It's a pleasure to be here. Happy to kick off day 2. I'm going to tell you about the emerging science of machine learning benchmarks, and specifically the question, why does the machine learning community work and make progress? And this 20-minute talk is pretty much everything we know about it, okay? So I'll keep it short. Many of you have seen this quote, the only principle that does not inhibit progress is anything goes, as Paul Feyerabend argued, and you might disagree or agree, but it's certainly true that machine learning as a community has always embraced the anything goes. Since its roots in pattern recognition and cybernetics in the 40s and 50s, it's tried pretty much everything, and it's led to great success, okay? So I'm not here to tell you it's a bad thing. I'm actually here to tell you it's probably a good thing. It's led to all these marvelous advances in the field. But there's one thing missing. It's not just the anything goes. There's also another component to tame the anything goes, and that, if you think about it, is the idea of a machine learning benchmark, okay? And it follows what the philosopher Strevens calls the iron rule of modern science, that all disputes between scientists must be settled by competitive empirical testing, okay? And he wrote a whole book about it. And the way we do this in machine learning is that we agree on a metric, such as classification accuracy. We agree on test data, test instances that we're going to evaluate our proposals on, and then we let people compete, and we rank whatever they come up with, okay? We call this a machine learning benchmark, okay? It calls it a benchmark, and follows this iron rule of modern science. The interesting thing is that machine learning benchmarks emerged. It's not like the founding fathers sat down and said, here is how it's going to be. This is sort of a paradigm that emerged over time, and in somewhat mysterious ways. It didn't follow any a priori theoretical framework, and we don't really know what it's even supposed to do on some level. It was sort of invented, or at least popularized, by DARPA grant managers to evaluate participants in their grant programs and compare them in a way that was objective and quantifiable. And then it was popularized by things like the MNIST digits classification benchmark in the 2000s, and it became sort of a machine learning mainstream thing in academia. And finally, it sort of exploded in popularity during the ImageNet era that was tied to the deep learning revolution of the 2010s and brought all sorts of new deep learning models into sort of the mainstream industry and academia focus. And now I would argue we're in a fourth era, which I call the polymorphic era, and it's characterized by like a massive benchmark plurality. We have thousands of different benchmarks. Many of them are multitask, so they aggregate across many different tasks, and many of them have also become dynamic, so the test data kind of change over time. So we're in sort of a new era of benchmarking. Okay, so this talk is not about the history, it's about sort of the outline of an emerging science of benchmarks that has sort of come about in the last 10 years, and some of the contributions that have been made to the science. And I'll give you some scientific takeaways from the ImageNet era, what we learned from those 10 years of ImageNet. And then I'll talk about some risks of the polymorphic era. So now that we're in this multitask benchmark setting, what are the things that are problems with this kind of paradigm, okay? And I'll wrap up by arguing why we need a science of benchmarks and why I think it actually fits in really nice into this machine plus minus behavior, area that we're starting here, okay? And so the way this started is actually with a mistake. Okay, I argue that this sort of science started with a mistake, and the mistake was to assume that benchmarks are just the holdout method, and you'll often see this, that people are, oh, it's just the holdout method, okay. What's the holdout method? The holdout method is a form of data splitting. You take your data set and you split it into two parts. One you call the training data, the other you call the testing data. You apply the anything goes principle to the training data, really no constraints whatsoever on the training data. But then you rank the models on the test set in the end, okay? And I say in the end because ideally this test set should be kept in a vault and be brought out only at the end of the data analysis. So you can read in one of the most popular machine learning textbooks by Hasty, Tipshirani, and Friedman. So the test set is supposed to live in a vault and only come out all the way at the end of the competition to rank these models. And this is for a good reason, because under this vault assumption, the test set has exponential longevity, okay? That sounds like something Silicon Valley billionaires are trying to get, but I just mean that the number of model comparisons is exponential in the test set size, okay? So if you have n data points, you can in principle compare an exponential number of models on the test set, okay? So it's marvelous, but it requires this vault assumption. You have to keep the test set in a vault, only use it at the end. Okay? So this is important. The empirical reality, however, is completely different. It couldn't be more different. The test set is anything but in a vault, okay? So there is a growing machine learning community of researchers that continually proposes models and looks at the results on various test sets and refines the models, and there's this ongoing feedback loop of model evaluation that characterizes machine learning science. To give you an impression of scale, MMLU is one benchmark. How many of you have heard or used MMLU? All right, 10 people roughly in this room. MMLU is just one benchmark data set in machine learning, and it was downloaded, I checked this, 5 million times in the last month on a platform called Hugging Face that goes by this emoji. And this is like just one benchmark data set in 1 month, 5 million downloads. If every download is one evaluation, that's at least 5 million evaluations, 60 million per year, one benchmark, one platform, okay? This is the scale we're operating at, and it's just 14,000 data points, okay? And so what's more important here, it's not just the number of evaluations, it's also how we do it. Machine learning is inherently adaptive. We look at the test results and we use them to improve our models. So there's this closed feedback loop between the model builders and the test set, and that's how the sausage is made. And this form of adaptivity, so we call this adaptivity, that you adapt to the results that you've seen, breaks all guarantees of the holdout method, okay? And in fact, you can show very simple examples where you only get linear longevity. So you could only support 14,000 downloads instead of 5 million, okay? So you would burn through your data set very quickly. This is something we recognized 10 years ago. We're quite shocked by it, and it launched sort of an area of like ways of trying to fix this. Okay, so this might be a bummer, but if you look at it sort of in practice, empirically, there is this sort of phenomenon that test sets live for a long time, okay? So here is a picture of the ImageNet classification benchmark. It's the ILSVRC test data from 2012. And here's a plot from Papers with Code. That's a platform that gives you code to run models on these kind of test sets. And it looks at all the models that have been proposed and their accuracy. And as you can see, this data set was created in 2012. And up until 2020, it supported lots and lots of like robust model improvements, okay? So it had a lot of lifeblood in it 10 years after it was created, and it's still being used very actively. So there's this empirical phenomenon that these test sets just stick around for a long time and are actively being used. So ImageNet has been used at least for a decade of model development. So this begs the question, should we trust the model rankings that come out of this benchmark? Are they reliable? Are they valid? Do they mean anything? Or have we simply sort of overfit to the test data? People wanted to find out, and they created a fresh test set for ImageNet. So they've recreated the test set creation process for ImageNet, collected a fresh test set carefully, and they found that the model rankings were actually preserved, okay? So the model rankings that you got out of 10 years of hacking away at this data set were actually valid. They were actually correct. If you, created a new test set, you would see the same. The same is true for MNIST, which is even older. That also works. For Kaggle competitions, all 200 of them or whatever, for NLP benchmarks and so on. We've tested this in a number of cases. It always comes out this way. It's what I call the phenomenon about the internal validity of the iron rule. Beating the previous best model replicates in similar conditions. If you recreate a test set, if you do something very similar, you're likely to see the same model rankings. So beating the previous best is something that replicates to similar conditions. It has internal validity. And we can even prove this. We did some theory about this and the sort of regularizing force of competition. Let's make a mathematical assumption, which I call the iron rule assumption, which is that researchers only care if they beat the previous best. And you can make this formal. Let's assume this is how researchers operate. They only look at their results if they significantly improve over the previous best. Let's make this a mathematical assumption. Then in a joint work with Avram Blum, we showed that assuming this iron rule, the benchmark data has exponential longevity. Okay, so if you assume that researchers only care if they improved over the previous best or not, you can actually recover this exponential longevity of the benchmark data. In other words, the takeaway is the iron rule is nearly as good as the iron vault. Okay, so this idea of competition and the seeming ignorance of the researchers that they only care about beating the previous best, that has a powerful effect on the longevity of benchmark data and justifies this excessive benchmark data use. Okay, so it's almost as good as this old-fashioned iron vault assumption. You can think of this as like a way to design benchmarks by limiting feedback that you give to participants. That's sort of the prescriptive use of this result. But I prefer to think of it as something like a natural algorithm, something that the community already implements on its own, like a principle. That the community only cares about results in this way, and so that's why these benchmarks live so long, okay? So that's a bit of theory we can do about this, and we found many other such socio-technical forces behind benchmark longevity. There's competition, which I just mentioned, but collaboration also works. If you share your code, that also has a regularizing effect. And even the cognitive and behavioral biases of data analysts can promote benchmark longevity, as we showed in a paper a while ago. And some of the mundane data set artifacts, like what classes you include and how many of them, that too can promote internal validity and longevity of benchmark data, okay? So this is kind of a fascinating thing that there are these things that are not purely statistical. They're about the behavior of people and how they interact with these benchmarks that promote the scientific well-being of the community in ways that we didn't recognize at first at all, okay? So there's a talk about this if you care. You can click on the link. I don't know. Maybe we'll share these slides, then you can click on it. Good. So what we know now at this point is that model rankings replicate on similar conditions. This is pretty good. We know some sort of internal validity story. Benchmarks tend to replicate on similar test conditions. Let's ask a more daring question. Do model rankings replicate on radically different test conditions? What if you go from one set of conditions to a completely different test environment? Are model rankings preserved? Okay? And so we wanted to find out, and we designed an experiment to figure this out. We call it the image not experiment, okay? An O instead of an E, image not. And here's the idea. Image not is an anti-replication of ImageNet in the sense that it has the same scale and diversity as ImageNet, but it's different in every other regard, okay? So it's like as different as we possibly could make it from ImageNet, subject to having the same diversity and scale as ImageNet. It's like an anti-replication, okay? When ImageNet was carefully created by humans and multiple annotators per image, and the community has studied this process to death at this point, ImageNet is just a quick and dirty web crawl where we selected images based on like which words appear in it and the captions around the images. Complete junk. You look at this, it's absolute junk, okay? This data set it just looks like complete junk, and I have some pictures that I could show you later, but I'm almost embarrassed to put them up, okay? So it's just what you get when you randomly crawl the web, okay? And so we retrained all key architectures from the ImageNet era on this junk data set from scratch and evaluated them on this junk data. And we asked the question, are the model rankings preserved? Does this junk data set give you the same scientific judgments as ImageNet? The answer is yes, okay? The rankings are completely preserved. AlexNet ranks lowest. That was the first architecture proposed for ImageNet, the big breakthrough in 2012, or 2014, I guess. And so you go on from there. VGG improves over AlexNet, DenseNet over VGG, ResNet over DenseNet, and so on. The model rankings are preserved. It's the same. But it gets better. The relative improvement over AlexNet is about the same, okay? So how much you improve in accuracy in relative terms over the previous best is also kind of preserved, okay? So for all practical purposes, to compare models, this new data set is just as good as ImageNet. It tells you the same things, has the same scientific takeaways. It tells you the same things about which model is better than which other model, and it's a complete junk data set, okay? So what can we learn from ImageNet? It's kind of fascinating. It says something about the external validity of the iron rule. It says that if you beat the previous best under sufficiently general conditions, it will likely replicate elsewhere. The only thing that mattered is that ImageNet was large and diverse. But the fact that it was noisy and junky doesn't really matter. It just means you beat the previous best in sufficiently general conditions, it will replicate in other sufficiently general conditions. This is a principle of external validity. And it suggests a kind of dynamic equivalence that from the perspective of model builders and the machine learning community, this gives evidence that ImageNet could have been anything of similar scale. Okay? We don't even need clean labels, which is shocking because we thought so much about like how important label cleaning and annotator cleaning and agreement is for like benchmarking. We don't even need clean labels. And this was maybe one of the most surprising aspects of this. So we did some theory on this as a result with Florian Dorner, and we can in fact prove that from the perspective of benchmarking, a single noisy label per data point works best for ranking models. Okay, it's the most efficient use of your label budget, a single noisy label per data point. Okay, and so that was also surprising, but we can prove this. Good. What happened to ImageNet? Well, large language models came along, and they changed things a little bit. So attention turned to sort of the capabilities of large language models around, the 2020s. And we were left from this ImageNet era with some growing skepticism about single task benchmarks. People were like, well, maybe we're just like deceiving ourselves, like having a single benchmark. Maybe we should have like many benchmarks. And so people proposed sort of an ecosystem of many different benchmarks and a diverse set of sort of multitask benchmarks, okay? So here are all the sort of big names in that game, Superglue and MMLU and Big Bench and OpenLLM. Big Bench, for example, has 204 tasks that test various capabilities of language models. One of the tasks is given a CMYK code, describe the color that the CMYK code refers to. So it's stuff like that. We're testing all sorts of things, and we're hoping that by testing all these things, we're sort of coming away with like a holistic and nuanced evaluation canvas about these models. That somehow by having all these different tasks and aggregating them into one, we actually, learn something more holistically about these models than what a single task benchmark could possibly achieve. Okay, so we wanted to understand multitask benchmarks better, and we, applied sort of a social choice perspective on multitask benchmarks, and you might already sort of guess where this is going. Tasks, these different tasks in a benchmark are voters. They get to vote on models. Well, models are the candidates, so they're up for vote. Every task can rank the models, so every task provides you a ranking of the candidates. And now the benchmark, the multitask benchmark, is faced with a problem of aggregating all these different rankings that come from these different tasks, these different 204 rankings, into a single ranking. That's the single benchmark ranking that everyone looks at, the leaderboard, okay? So benchmark system is a voting rule that has to take all sorts of diverse ranking information and aggregate it into one. And you probably already see where this is going. There's some like arrows impossibility type result lurking here. And we're going to see that actually there's an inherent trade-off between two very desirable properties in multitask benchmarks that I'm going to tell you in a minute, and you can't have both, okay? And in fact, it's quantitative in the sense that one is going to come at the cost of the other, and it's not a theory result. It's something that actually holds for the major multitask benchmarks that people are currently using, okay? So let's look into this, okay? This is the upshot, and let's look at some of the big multitask benchmarks right now. One of them is Stanford's Helm. It's a fantastic new effort to holistically evaluate language models. I guess that's what it stands for. And it takes all these, 2 minutes, okay, yeah, that's fine. And it takes all these models that, from industry and evaluates them on a bunch of scenarios. And it looks at something called the winning rate, okay? How often models win against other models, okay? This is the winning rate. And you can compute the winning rate of a model just by having individual task rankings. You don't need any metrics or any numbers. You just need to know how often you come up higher than another model. That gives you the win rate. And so this is what we call an ordinal benchmark, because it just works from ordinal information. It aggregates ordinal information. Another popular benchmark is the Open Language Model Leaderboard on Hugging Face, which just averages accuracies, okay? Just like takes all the task accuracies and averages them out. That's what we call a cardinal benchmark. It sort of averages out numerical scores, okay? So these are slightly different, so we need that distinction. And the two key properties that I'm going to put forward are sensitivity and diversity. Sensitivity is about changes in rankings in the benchmark due to irrelevant task transformations, okay? You don't want that, okay? You don't want that your benchmark sort of changes with irrelevant task transformations. One irrelevant transformation for ordinal benchmarks is the introduction of weak models, okay? You don't want that if you introduce a really bad model on Helm, I upload a really bad model to Helm, that somehow the two top contenders switch, okay? This would be terrible if like I can perturb the top two contending models on Helm by uploading some junk model, but that's absolutely possible, okay? Second, for cardinal benchmarks, because they're averaging out metrics, you would hope that, it's like stable under transformations of the metric. So if I just relabel my accuracy numbers, 75 becomes 80, 80 becomes 85, that shouldn't make a difference because the ranking of each task is the same. I just renamed the numbers. It doesn't matter, right? I just like relabeled the accuracies, just a monotone transformation. It's conceptually the same as making the task harder but equivalent. That also shouldn't matter. We can always minimize sensitivity by just having a single task because a single task just has one ranking. So we can always set sensitivity 0. So the other key property that we need that people want out of multitask benchmarks is diversity. We want high variance in rankings. That's the whole point why we have multitask benchmarks, to have a diverse set of rankings, okay? So we have sensitivity to irrelevant changes and diversity. And these two are at a trade-off, okay? And so here's the picture that we get. If you plot all current multitask benchmarks, these are cardinal benchmarks, in this diversity versus sensitivity plot, they all lie on a line between constant, a benchmark that has one immutable ranking that can't change, and random, a benchmark that has a completely random benchmark, a completely random ranking. And not one of them can escape this trade-off, okay? So they all strike some trade-off between diversity and sensitivity that lies on this line between constant and random, which means that, diversity comes at the cost of sensitivity to relevant changes. If you want a very diverse multitask benchmark, the only way to get that is by paying for it in terms of sensitivity, okay? There's no other way to get this. It's in some sense, there's this one-dimensional notion of multitaskness, and you can't escape that trade-off. Okay, and here is just to demonstrate visually the effect of irrelevant changes on OpenLLM and Helm. So here we just take, let's say, how much can we perturb the top 20 models by adding like a model that is like at rank 50 or 49 to the benchmark, okay? So we just add a weaker model to the benchmark and look at how much we can perturb the results, and as you can see, it goes all over the place, okay? So these rankings between these models can change quite a bit. GPT 3.5 Turbo and Helm could drop many ranks just by introducing some other irrelevant model to the benchmark. Okay, so it's pretty unstable. Good. Let me wrap up. The ImageNet error retrospective that I sort of gave you is that there are these two laws of the iron rule, internal and external validity. We understand them empirically a little bit better now. Theoretically, you only understand the former but not the latter, and I think that's a really interesting problem. And then I talked about this polymorphic reality that multitask benchmark diversity comes at the cost of stability, okay? And so I hope that you appreciate that some of the intuition we had about benchmarks was not correct, and that some of these findings were not at all clear from like first principles or a priori before we started doing this. And so that to me is like a strong indicator that we need this kind of science of benchmarks that figures out these problems. And I hope that venues like these will also be a platform for that kind of work. And remember, machine learning is anything goes plus the iron rule. Okay, that's the secret sauce. All right, thanks.
Okay. First of all, there's so much to unpack in Moritz's talk that I'll try to slow down and just say a couple of things about foundations of foundational models. Let me start with a particular perspective that I like to look at when I think about how AI systems have been evolving from machine learning to deep learning to foundational modeling. I see it as a little bit of a triumph of lazy engineering, right? Like at each level of things, you want to have designers do fewer things and get more out of it, right? And what I'm going to argue is that these triumphs have some fundamental tragedies associated with them as well. And one of the tragedies of going from traditional AI to machine learning is, I'm going to argue, is fairness. With deep learning, there's a tragedy of explainability. And with foundational modeling, I suspect that there are some tragedies, but we are yet to discover them. Now, I'll explain what I mean by these tragedies being a bit more foundational in the next couple of slides. So let's start with the triumph of machine learning. So, if you went back to 1960s, traditional AI was basically programming a computer, right? So the traditional model was imperative programming, where you essentially describe the procedure for solving a task. Like you would literally write down the code. That was the traditional AI. With machine learning, essentially, there is a sort of a shift in the way you do programming, right? Which is declarative programming. Instead of actually telling the computer how to solve it in a step-by-step process, you declare the objectives for your task, and then you expect the machine to find the optimal solution for it, right? This is how traditional machine learning works. And the tragedy of this is, is basically defining the right objectives, right? And this is particularly hard when some of the objectives that you want are those that are expected to capture societal norms and laws, contracts and regulations, and user cognitive abilities and behaviors, right? This is the fundamental problem with fair machine learning, which is what a lot of people have been working on, which is how do you actually capture the sort of societal desiderata into the objectives when you're training these models. So we have made quite a bit of progress. So for example, an ImageNet search for CEO, image search for CEO on Google was yielding this kind of result. So after a decade of research, we ended up with this, right? So this is the AI model of, generative AI model of Google. When somebody said, generate an image for a 1943 German soldier, it generated this picture. Now, some might think that in the future, this would be a nice picture if it said, generate an image of German soldier in 2043, but probably not in 1943, all right? So it captures the difficulty of actually capturing the right objectives. Now let's move to deep learning. Now, with traditional machine learning, one of the things that designers would do is at least feature engineering, right? Like, so when you define your deep learning model, you actually define the features. In the traditional machine learning, which is before deep learning, you would actually define the features from your input data that you would want your model to use to solve the task. With deep learning, feature engineering has been replaced with representation learning, right? You just declare the objectives for your task. And once again, you're expecting the machines to extract what features are relevant and useful from the input data. And the tragedy with this, of course, is the alignment problem, which is now the machine is picking up some features from the input data, and you have no idea whether it actually aligns with what humans might pick up, right? And the immediate problems that you have with this is lack of robustness and vulnerability to adversarial attacks. And these are some fundamental limitations, and this is what I mean by a tragedy, an absolute fundamental limitation, because when you cannot align these things, okay, the animations are kind of messed up. I don't know why. I guess it's because of the change of the laptop. But in any case, so you would have seen these examples like this, adversarial examples, where you add a little bit of adversarial noise, and all of a sudden, the picture would change to something completely different. And this is a much deeper problem and a fundamental problem in terms of it's very hard to fix this one. So for example, here, what I'm showing are images of robustly trained machine learning models, the state-of-the-art robustly trained machine learning model. And all those images of dogs are, from the perspective of the deep learning model, identically represented. That means the deep learning model thinks all of the pictures look exactly the same, whereas as humans, we wouldn't think that, right? So fundamentally, there are limits on to what extent you can even explain a model when the representations are different. And I think this is something that's a much deeper problem. Now, let's come to the triumph of foundational modeling. So here, once again, in traditional deep learning, whenever you wanted to transfer the deep learning model to do another task, you would do fine-tuning, right? So you would retrain certain parts of the model, so that you would adapt the weights and the representations for each task. With foundational modeling, one of the triumphs seems to be that we can get away with what is called as few shots, right? Few shot learning is one where you just give a few examples in the context, and it figures out what the task is, right? So this is the thing that is engaging a lot of people. So the word foundational, at least to me, the way I interpret it is these models are supposed to have a representation of a world's knowledge, and then they're also capable of figuring out patterns in these representations, right? So this is the few shotting thing. Now, what I'm going to, what I'm going to argue, so in terms of the tragedy of foundational modeling, I still think we don't know what the deeper fundamental limits are. We see a lot of problems with them, but I still think we are yet to find what are the fundamentally unfixable things with foundational modeling. But to get there, I think we need to have better foundations. And what I mean by this is today, if you look at a lot of work that is being done and being discussed and presented, we have a lot of observations about the behaviors of these models, but then there is a lot less understanding of the underlying cognitive processes. And what I mean by this is thinking in terms of how do you explain the behaviors from the perspective of information processing, in terms of how information is being received, processed, organized, stored, and being retrieved, right? And this is what I'm going to argue for. And this brings me to the topic, which is one thing that I feel that we need to do to get to better foundations is to understand certain phenomena. And here are 4 phenomena that we try to understand better. One is learning by rote, which is memorization. The second is learning factual knowledge. Third is learning via examples, that is in-context learning. And the fourth is learning formal grammars. Now, there is no reason to think that these phenomena would cover everything that is of interest. No. In fact, these are just 4 simple phenomena that we felt we could actually get some traction by looking at them. So let me just give you a couple of examples of how we're going about these things. So let me start with memorization. I just can't seem to get this one. Okay. So the phenomena of interest is memorization, and the question that we want to ask is, do LLMs memorize, or how would they memorize training data? Now, let's think about what do we mean by memorization here. So this is a definition that I picked from Wikipedia. So it says that memorization is a process of committing some information to memory in order to recall later. Sounds interesting. Now, why study LLM memorization? There are a couple of different reasons for this. One is privacy concerns, which is that there are people who believe that when LLMs are trained over the web corpus out there, it might actually memorize some of the data. And so there are privacy concerns with respect to information leakage or membership inference. And there is also concerns related to reliability of generated data. Now, in some sense, if you don't want LLMs to hallucinate, you want an actual reproduction of facts. That means you would actually want it to memorize. But on the other hand, if it was memorizing, there are all sorts of issues related to copyrights and crediting authorship that would arise as well. Now, this is the motivation for studying memorization. So in terms of prior work, there's been quite a few of these. And they focused on quantifying memorization. So at a high level, the way they work is they say, if you take a token string, some sequence of words in the training data, and to test if it is being memorized, what you do is you give some prefix of the string and then see to what extent it can generate the rest of the string. Okay? Very simple test. Now, there is a whole set of measures that have been proposed that all are about understanding to what extent means, right? Now, the argument that I would make is that in the process, they're actually quantifying privacy risks, but it is far from clear if they're actually quantifying memorization. Because here is a simple way to think about this. Suppose you give a mathematical sequence, like a Fibonacci series, and it completes the remaining elements of the series after you give the first 5 numbers. Do we know whether this is because of memorization or because of reasoning? And similarly, there is also in-context learning that we need to distinguish memorization from. So here, simply think of a replicated string. Think of a string, and then you replicate it. Now, if you actually go through the process, when you're generating the second part of the string, just because of in-context learning, it is going to recollect it accurately. So the question is, can we even, or do we even care about distinguishing the phenomena of memorization from the phenomena of reasoning and in-context learning? Because currently, the way we're quantifying this, it doesn't make the distinction, okay? Now, the question is, how can we do this? How do we study memorization? So here is our simple idea. Our idea is to basically take random token strings. And what I mean by a random token string is one where each token is generated through a random sampling of a probability distribution over a set of vocabulary, right? And so in the process, what we did was we took several different types of these random token strings. They vary in length from 16 to 1034 with different lengths. We tried this on different models, and the vocabulary, that is the tokens that comprise of these things, we varied them. Now, the simple experiment that we did was we took these strings, we took the LLM, we repeatedly iterated over the strings. And after each iteration, we were trying to see to what extent it can recollect it accurately. Now, why did we do this for random token strings? Because if you think about it, if an LLM is able to recollect these tokens, it cannot be due to reasoning or in-context learning. It cannot be due to syntax or semantics. The only way in which it would be able to recollect it is because it has learned by rote. And that's the reason why we went for this synthetic setup. Now, oops. So we did this, and so let me pose the following question to you, which is, we studied various different phenomena, and one simple question that we started with is, are some strings more memorizable than others? And so what we mean by this is, here are two strings. They're both random token strings, one generated with just A and B, and the other generated with from A to Z, right? Both of them are similar length, 14 characters long. Now, if I were to ask you to try to memorize the first one versus the second one, how many of you would find the first one easier to memorize? Okay. How many? Okay, so since most of you said that the first one is easier to memorize, I'm going to assume that the second one is going to be harder. Now, what about LLMs? How many of you think that for an LLM, the first one would be easier to memorize than the second one? Very few. Okay. Now, why? Any hypothesis for why? Yeah, you raised your hand. No? Okay, so it's actually, I'm actually amazed that so many of you got it right. It's actually true, but then you can ask yourself the question, why is it for humans the first thing is easier to memorize? And why is it that for LLMs, the second thing would be easier to memorize, right? And in fact, those are the types of questions that we wanted to ask, and that's the real motivation for conducting this experiment. Well, let me show you quickly a result. So this is an experiment where we took the Pythia language model, and other models exhibit very similar behavior. What I'm showing along the x-axis is the number of epochs, that means number of iterations over the string to memorize. It's literally like a human would repeatedly go over the string to memorize them, right? And then along the y-axis is the accuracy of recollection of a token string, right? And you see the different plots there, and they are for different vocabulary sizes. That means the blue one is when the token string is made of just A and B, and the purple one here is when the token string is made out of 26 characters, A to Z, where you're randomly sampling from them. Now, you can clearly see that the smaller the vocabulary, the harder, meaning the smaller the alphabet size from which you're generating the token string, the harder it is for it to memorize. In fact, for the token string made out of just A and B, even after 100 iterations, it's still struggling to memorize. And equally interesting, if you looked at the very early region, after just a few iterations, you notice that there is a immediate jump in terms of to what extent they are able to accurately recollect. So what's actually happening here, and we verified this is the part where the model, after the first few iterations, has figured out that this is a random token string over a certain vocabulary size. And so it's actually getting the accuracy right in terms of predicting the probability distribution from which it's being picked. But it's in the second stage that it's actually going on to memorize. So the takeaway is, in fact, we showed that this is actually not even related to the alphabet size, but it's actually related to the entropy of the probability distribution from which we're picking the next token. So consistently, the lower entropy strings are actually harder to memorize. Now, there is a question of why, and what is this revealing about the model of memorization that LLMs are following? Those are the deeper questions that are worth asking. And in the interest of time, I'm just going to move on to the second phenomena, So Till Spiker, who's here, he's the student who led this work. There are lots of other interesting observations about memorization like this. But let me talk about another phenomenon of interest, which is latent knowledge, which is how do we estimate facts? What I mean by latent knowledge is how do we estimate what real world or facts about real world entities does an LLM know? And by facts, I mean here something like Einstein, birth year, was born in the year of 1879. So very quickly, why estimate latent knowledge? Because there's lots of concerns about hallucination. And if you don't want an LLM to hallucinate, at least the minimum requirement is that it should actually know the real fact. Now, let me make the immediate distinction. Knowing a real fact doesn't mean that it will not hallucinate, but at least it's a necessary condition to not hallucinate. And the question is, we want to estimate what fraction of real-world knowledge is latently embedded in the models. So, oops. Now, there's been a lot of work on prior work on knowledge estimation, and at a very high level, the techniques that were used is one of prompting. So you want to know if whether an LLM knows when Einstein was born. Just simply ask the LLM. Now, the problem, as many of you might know, with any sort of standardized testing, is that there is a problem with test administration and test scoring. So for example, with prompt engineering, you can actually get the LLM, you can actually torture the prompts to get both the correct and the wrong answers. And there is all sorts of problems with these kinds of prior approaches, which is that they don't even define the space of prompts from which you can pick them, right? And then there's all sorts of side channels. For example, for the relationship X holds the position of, they found that it's actually better to probe the LLM with X is elected to the position of, right? Now, elected is already leaking some side channel information, like that the position is definitely not that of a professor or whatever. And similarly, there are problems with test scoring, which is often you are evaluating the meta-linguistic judgments of the models rather than the actual knowledge. This is a deeper topic that we can discuss it more in the Q&A if someone is interested. But let me just quickly point out what we tried to do. Our idea was ridiculously simple. That is, to use in-context learning. Suppose if you want to figure out when Einstein was born, just give the prompt Planck, Max Planck, space, birth year, comma, Otto Hahn, space, birth year, Einstein, space, what, right? Now, this is a very simple approach of doing things, and if you're wondering why somebody hasn't tried this before, it's probably because what is actually happening here is we are using in-context learning to get the LLM to pick up the pattern itself, right? So rather than asking what the relationship is, we are expecting it to pick it up from the examples, just like we would do in an IQ test. And here is the highest order takeaway. It turns out that our approach outperforms all the existing prompting approaches. Where there have been a lot of works on human-generated prompts, machine-mind prompts, and we beat them all with this very simple way of extracting knowledge. There is a question of why, and we will leave that for the Q&A and other sorts of things. So I wanted to conclude this by simply pointing out, this one, which is, I think if we want to go towards better foundations, I think there are very simple phenomena that we can probe quite deeply and try to get some insights about. Thank you.
Okay. So we have also microphone ready in case people want to ask questions. So thanks for the engaging talks and a lot of insights and things to ask. I think also like people from the audience will have a lot of questions. I will start from like a general question because both of you were talking about like evaluation and how to evaluate this type of tools. So do you think that we are, so like this is, it was something that I I keep thinking, when we are evaluating this type of models, we are evaluating something that is similar to a natural phenomenon, an artificial phenomenon, or are we doing something else? Because it is not a theoretical evaluation, but it's a measurement that we are doing. So it seems to me that you are trying to measure a phenomenon through repetition, through an extraction of some statistical indicators, some values. So I would like to ask you, what is your view on this?
Krishna used the word phenomenon more often than me, so I'll hand it over to him for now. But maybe that's unfair. I think there's this question in machine learning, what are we even studying, like in sort of in investigations about machine learning, right? For instance, is every I mean, there are all these things that are happening. Is everything a phenomenon? What are we trying to understand? Memorization, is that something that we can sort of define and understand empirically? And then how do we ask the right empirical questions to not just make this some sort of freestyle exploration, but sort of at the end of the day have some sort of hypothesis that we can try to state and maybe refute. But I find that very challenging, and I think on a number of fronts, evaluating machine learning is an extremely challenging aspect, and also saying what it does. So the one thing I'll add maybe is that part of why we're limiting ourselves is because we understand some of these questions as purely technical questions, right? And that we sort of don't look at how the community operates, but we're looking at sort of the micro level of like, here's this neural net, and here are these representations, and if I toggle this kind of prompt, something will happen. And I think this is maybe, from a sort of empirical perspective, I would like to zoom out a little bit, and also maybe in the theme of this conference, try to understand sort of the more macroscopic patterns in the way that the community operates.
Okay.
I don't really have that much more to add beyond what Moritz said. I guess maybe with respect to the, I would only add one small thing. So one thing that I feel it might be useful to understand with respect to LLMs is to try to explain their behaviors, to try to understand their behaviors in information processing terms. Mm-hmm. At least that's the thing that I find interesting and attracted to. Like if you can explain, so there is this behavior that they exhibit that certain types of strings they memorize better than others. Now, what is that revealing about how they might be working, right? Like, so it might not be a precise mechanistic explanation. I feel that may be too hard to get to right away, but at least what is it revealing about the model that can we at least have some models in terms of information processing about how the memorization is happening, right?
So in relation to this, I think there is an interesting question here, because there is a mixture, in my opinion, also from your work, between some sort of ranking, like sort of measurement, and then you rank precision, you rank correctness, you do performance evaluation with some statistical indicator. And then there is also another aspect that is probably more traditional science, if you want like sort of Karl Popper's science, so where you set hypotheses and you try to see if they are falsifiable or not. Do you think that this approach is still valid with models that, like foundational models, where we understand certain properties, or like the definition of the properties themselves might be difficult? Because, for example, you need to define, so it is a definition that might be a definition not subjective, but is a definition that might change. For example, the fact that you have, I don't know, memorization. You can define memorization in different ways. So how do you think we should proceed in terms of evaluation? Because this is a discussion also like around people, like to say, okay, if we want a good science should essentially at least linked to the canon or to the way people essentially perceive like the scientific validity of certain findings.
Yeah, maybe I'll just give one example that's recently come up in the language model context. And that's the idea of an emergent capability, right? And I think OpenAI certainly emphasized this aspect of large language models quite a bit. That is sort of this inherently unpredictable aspect to what they can do, and the only way to find out is to really let them build these giant models and see what they can do, and it could be anything. And also you don't know what's happening elsewhere because we don't know at what scale we achieve what kind of behaviors. There was recently a paper out of Stanford by Ryland Scheffler and Sami Kwejo that I really liked that sort of challenged this belief a little bit, and it's called Are Emergent Capabilities a Mirage? And they put forward the idea, is I think intriguing, that maybe if you change the way you evaluate these models, if you change the metric to something different, these things that seem discontinuous and unpredictable become more predictable, and that somehow by changing our evaluation metric, we actually make these things more predictable. I thought that was a fascinating take on a complex subject, which shows that, yeah, there can be progress on how we, discuss what these models can do, and how we also argue about some of these meta properties like emergent capabilities. And I do think the community is certainly capable of making progress on that. Yeah.
Thanks.
Yeah, I just wanted to add one small thing there. I think at least sometimes the problem that I perceive is sometimes when people talk about what LLMs are capable of doing in this thing, I think there is a lot of different words that are used with very specific meanings, right? So you were asking, I think you may have mentioned this, that is there one way to think about memorization? Probably not, but I think the important thing is to make sure that when somebody is saying something, we actually understand what they mean by it, right? Yes. Because I think these days there is a lot of things that are attributed to LLMs, which, clearly they have a lot of they're exhibiting a lot of interesting abilities, and they have tremendous societal applications. This is all fine, right? But from the perspective of academic research, at least, I feel like one thing that would be nice is if we knew and if we were careful a little bit more about what we were actually measuring, right?
Yeah. I see. So one take from this might be that maybe also the definition of metrics might be something that we should aim for. Metrics or at least performance indicators, an equivalent of an F1 or some sort of confusion matrix, as people were doing, I don't know, in the past for this type of, where everyone essentially understands what this means, I think might be something potentially interesting. We have already a queue there, so I think we needed to go to the queue. Yeah.
This is a great discussion. I don't know if the microphone's on, so I'll just talk. You can hear me okay? If I see you again, Moritz. So I wanted to ask two questions. The first one was actually a tension that I saw in your two respective talks that I wanted to elicit. If I kind of understand it right, it's kind of like, Moritz, you kind of had this kind of micro and macro factors that shape the science of benchmarks, right? And if we get those right, we kind of make a lot of progress. The field kind of guides itself towards better designs of systems. But in your talk, Krishna, you mentioned this point about failures. Fairness being a failure, kind of lack of robustness. So I'm kind of curious, right? If we talk about some of these kind of meta effects of what we want our properties of our systems to imbue, does this kind of micro and macro factors actually lead? Do we need a different model to achieve it, right? Or is it a kind of a limitation of the benchmark framework, right? And I'm thinking fairness in particular because I know, yes, So then the second question is, right, so both of the talks were really focused on evaluations of, let's say, models in situ, right, in isolation. But I think and a lot of things that we've mentioned, we've talked about, I think a lot of people are interested in, obviously systems that are used in real world settings, right? And so when you add humans into the loop, how do you think about that framework for kind of improving the quality of your systems? Because ultimately, I think a lot of discussion around alignment is actually a question of not just the model in a vacuum, but obviously when you're engaging with multiple stakeholders and hoping to try to align a system towards better kind of pro-social behaviors. So I'm just kind of curious about those two tensions that I kind of saw in the talks today.
Yeah, so excellent question, both of them. I'll start. by saying that, you're correct, and Krishna and I debated yesterday for 4 hours, so, the tension is real. So we have different views on this. But you make an excellent point that everything I said was sort of about model rankings narrowly construed, and it does not apply to things like fairness evaluations, which are, of course, of vital importance. And some of the lessons I was sort of talking about do not hold for things like fairness evaluation. Certainly, having like high-quality annotations could be absolutely vital for like all sorts of fairness evaluations. And so this is an excellent point you're making. And so I do think when we talk about societal sort of implications of these models, this is a different story. I was sort of talking about the nitty-gritty competitive aspects of model ranking, which I find sort of interesting as a scientific subject. And so that's what I wanted to focus on, which is not to sort of try to like say that the other thing is we should stop caring about it. I'm still very invested in these things. So.
Yeah. I was going to say, I'm sure, I know you do. It was actually, the curiosity I have is that obviously a lot of the polymorphic benchmarks do have a fairness component. Helm does, right? So Big Bench does. So this actually is an interesting question of like, obviously a merger between these kind of areas of focus, right? You are going to start seeing some of these elements in these bigger benchmarks. And so,
Absolutely. There are some touching points. And for instance, the arrows type stuff does apply to Helm fairness as an example. So there's some of these things transfer, but I just wanted to make it clear, sort of the caveat about what I said. The second question is also excellent, and I'll talk about one work that I didn't have time to go into. It's about dynamic benchmarks. It's joint work with Ali Shirali and Radia Dabebe, and we studied this idea of like putting humans in the loop of sort of like evaluations, where you start with a bunch of models, you let the people find failure cases, you throw the failure cases into the thing. And so we had this somewhat sobering result that progress in these sort of benchmark designs can stall after a few rounds. And we tried to sort of suggest benchmark designs that might mitigate some of these limitations. And then recently, Reddy had pointed out to me that a lot of this stuff also applies to, like what we did also applies to ideas like red teaming. And now you see more touching points of these two topics, right? And so I think by studying these sort of dynamic benchmarks, we can also make progress on understanding your humans in the loop, in the evaluation loop. But it's a very challenging subject that I also find quite difficult to say anything reasonable about.
So I think Moritz answer is quite extensive, and it covers many of the things. But a fantastic question. I completely agree. So in these talks, at least in my talk, at least, I was focusing deliberately narrowly on one thing to point out that even some simple things about these language models are not well understood, while we tend to attribute a lot of interesting characteristics to them, right? And so that was the point that I wanted to make. And so deliberately, for the rhetorical reasons and to get the focus on that, I narrowed it down to just this particular topic. But in general, I would completely agree with you that the more interesting and challenging questions would arise when these things are used in practice together with humans.
Thank you.
Okay. I think we ask a question now here, or there was, okay, please ask the question.
So one of the questions I had was in talking about benchmarks, a lot of it was about sort of retrospectively looking at things people do and then saying, like, actually, those things that you thought might have been a problem sort of make sense from some perspective, maybe because there's a fundamental trade-off, or because having this rule actually helps you have more longevity and things like that. Could you say more about the aspects of what people do for benchmarking and evaluation that you think are the most problematic in the community right now? And maybe you started to say a little bit about that related to the dynamic benchmarks. And then also relatedly, like when we start to think about evaluations that aim not just to rank things well, but also to give us some indicator in an absolute sense, like whether we should take some action. Is that, to what extent is some of the science of benchmarks work that's emerging addressing that problem as well?
All right, yeah, I'll start with the first. I'll point you to one paper that inspired us to do this dynamic benchmarks work, and it's a paper by Sam Bowman and I think George Dahl. It's called "What Will It Take to Fix NLU Evaluation" or something like that. And they go over all sorts of like, concerns they have with benchmarking and evaluation in natural language processing. And I think it does a really good job laying out some of the issues from the perspective of like, Sam has been creating all sorts of benchmarks for a long time and put a lot of experience into this. And in particular, I think he's very negative on this idea of dynamic benchmarks and thinks this just sort of leads, models astray and like steers them towards like sort of artificial cases, and they start to forget like more important tasks and doesn't actually improve model performance. And so I think I do see a lot of issues or questions in terms of how we should pull off something like a lifelong benchmark or like a sort of a dynamic, everlasting benchmark that kind of grows and adjusts to the task. So I think the biggest conceptual challenges to me are in this dynamic setting where we have either humans in the loop or some sort of like continual evaluation. There I really don't, and I'm not judgmental about it. I like the fact that people are trying out all these things, right? I think they should continue trying out all these things so we see what works. But there it's really hard for me to understand what might even work well. I don't know. So I think the dynamic setting. May you repeat, could you repeat your second question?
Oh, yes. So, and then the second question was when we actually care about the absolute value of the metric in some sense, like maybe in the context of safety benchmarks, right? We want to say like, if we hit this point, then we're going to take some action before we release our model or something. Yeah. We're not just interested in a ranking of things. Yeah. To what extent is there, what would be your thoughts on sort of the science of benchmarks insights to keep in mind here?
Yeah, so to keep in mind, I think the interesting thing here is the actual numbers are neither internally valid nor externally valid. Okay, they just satisfy nothing. Even if you recreate the test set with the most care you could possibly put into it, you get completely different numbers. Okay, so you never get the same numbers, even if you undertake massive effort to recreate nearly identical conditions, you will get different numbers. And so I think that's why I moved on to like study rankings as sort of the object of investigation, because they're a lot more stable, okay? And so I think you could just get a very bleak picture if you look at sort of the transferability or generalizability of these actual like performance numbers. They're just not, you can't take them at face value because they will be different on any other thing. And so I think we don't quite know how to like, what to really do with an accuracy number like 84%. We just don't know what that should tell you. Is that good or bad? We don't know.
Thanks. We can move to the other one. And then we have one here. Still a bit of time. Yeah, please.
Thank you so much for two really captivating talks. I was especially fascinated by the idea that holding out a benchmark kind of might not make a difference for getting the ranking right. So as kind of a practitioner who also we're developing benchmarks, I'm wondering, how do I know whether a benchmark is sufficiently general enough? So that was kind of a term you used that I feel like was, that there must be a lot hidden in there. And then we also talked yesterday about kind of psychometric testing, theory of mind testing applied to LLMs, and obviously in psychology or psychometrics we have some idea of how to get a test to be kind of sufficiently general enough that it'll carry over even if a person has seen it before. Is there any transfer of those insights between the fields, or is what it needs to be sufficiently general for a benchmark really just confined to building a good benchmark?
Yeah. Excellent question. So yes, I sort of hid a lot of behind this term, sufficiently general conditions, and I hope nobody would notice. So no, you called me out on this. Yeah, so I don't know. I don't have a good answer to this, especially like, I mean, for ImageNet, for image classification, we have intuition about this now, but only with the benefit of hindsight, right? Now, if you come to me with a completely new problem and you ask, what should I do? It's much harder to say, right? And so I think I don't have a good question to that, or answer to that question in general. About the psychometric tests, I know of a recent work by Tom Sewer at my institute with a few other people about evaluating personality tests, or the sort of some pitfalls of using personality tests to understand large language models. And so I'm happy to send you that pointer, which I thought was like an interesting bridge between these fields. Yeah.
Thank you.
Thanks a lot. I think we have another question here, and then thanks.
Yeah, you mentioned that there's this cycle between or on benchmarks where sort of people update their model in response to the results that they get on the benchmark, but that doesn't necessarily affect the validity of the results because it preserves the rankings. One concern recently has been, I guess, that the benchmarks, like the actual data, might show up in the training data, especially of large language models. And I'm just wondering, has that the potential to affect some of these results, particularly, say, if one model has seen the data in its training data and another one maybe hasn't?
Yeah, absolutely. So this is the key point, the last thing you said. So if everyone used the same training data, I sort of don't care if there was data contamination in that data set, because it doesn't really matter. It just inflates the accuracy the same way for everyone, and it would just basically, it'd be an irrelevant change. It would make the task easier. It would just remap the accuracy numbers to something higher. The main issue arises when models have been trained on different training data sets, and these training data sets are more or less similar to a given benchmark. And then you lose the comparisons. That's a good point. Yeah.
Thanks a lot. So I have a question, like another question for Krishna about your test. So you have these measurements essentially between like machine and humans, and the result that you get essentially tells us something about the machines, but I think they tell us also something about humans. So like the way you memorize, for example, the thing that you presented. Do you have any insight about that? Like in terms of why is this the case? That it is harder for us, or so it is please.
So, for example, if we just took the example that I was giving about memorizing two different types of strings, I suspect, this is my hypothesis, which is many people felt that the string with just two characters, A, B, might be easier to memorize, perhaps because when you're trying to memorize it, they might remember it in from a compression perspective, right? Like they might say 2 A's followed by 4 B's followed by 3 A's or something. If that is the model of memorization, then the first thing would be much easier to remember than the second one, because in the second case, you have multiple different things. But if the model of memorization was based on, say, using partial prefixes to recollect the next token, that is, if you start asking the question, what is the minimum amount of context, like prefix, that you would need to recollect the next token? If that is the way in which you're doing memorization, then it would explain why the second one is easier to memorize. So essentially, from this simple experiment, what you can actually deduce is even though we may not know exactly how the memorization is working, you can construct potentially different candidate models for them. Like you could say, you could memorize it by, you could do memorization of a string by remembering for each position what character exists. Or you could do memorization using full prefix or partial prefixes, or using this kind of compression-based memorization. And you can rule out some of the models with a simple experiment like that and conclude that it's probably this is the one that is working on, right? But it's still, I would call it a model, and because we don't know at a deeper level what is going on. So with more careful experimentations, we would be able to refine our models further down the road in terms of understanding these things better. So that's the sort of thing that I was thinking about.
Yeah, I was thinking like as humans, seems that we have more bigger instruction set. We can do like some instead of just next token as instruction, we have also some sort of like summarization or compression instruction that let's call it instruction as a machine, because a Machine+Behavior Conference that is different from the.
But going back to your higher level question, I do think some of these things might reveal some interesting differences between how humans learn versus how LLMs are learning things, even though in terms of their behaviors, they might exhibit similar kinds of behaviors or different ones, right?
Thanks a lot. So I think we are at the end of the allocated time. So we'd like to thanks again the presenters.